Okay, let me get things started. Welcome to the 2009 Cesare Emiliani lecture. This lectureship is jointly sponsored by Ocean Sciences and Paleoclimatology, Paleoceanography. I've reversed those halfway deliberately. Okay, you're not hearing me very well. Can you hear me a little bit better now? Good. This is good to know, to learn about this microphone, because the next person will need to know this. I'm Phil Myers, chair of the Paleoceanography, Paleoclimatology Focus Group. John Farrington, chair of president of the Ocean Sciences Group, is down here. This lecture is held every year in tribute to the contributions of Cesare Emiliani, who is considered by many as one of the fathers, the founders of paleoceanography. In the spirit of tributes to people who are important in our field, we have a tribute to Jean-Marc Barnola to start things off, and then we'll proceed with the actual Emiliani lecture. And to present that tribute, Xavier Fan is here today, and I'll turn things over to him right now.
Thank you. Should I go ahead? Okay, so many you heard about that, but the 21st of September 2009, about 3 months ago, Jean-Marc Barnola passed away at Lamur, the small city he was born in Grenoble, close by Grenoble in France. Jean-Marc was 53, and he was certainly a great scientist for our community involved in paleoclimatic research. And during my PhD, I was a PhD student at LGG, the laboratory of glaciology and environmental geophysics in Grenoble in France. I had the chance to work closely with Jean-Marc. And on behalf of all colleagues from LGG, I'd like to just say thank you to AGU that gave us today this opportunity to have a few words for his memory. Oops. So Jean-Marc defended his PhD in 1984, and in 1985 he got his position at LGG and he started his research. I guess many of you actually knew him for having been the first one to reveal, this relationship between atmospheric CO2 and temperature over, climatic cycle. And in 1987, he published with others this really famous paper showing for the first time a CO2 curve from the Vostok ice core, the Antarctica Russian station. And this curve showed for the first time this strong link between atmospheric CO2 and temperature over full glacial, interglacial cycle. So later, Jean-Marc contributed to the CO2 and climate record, reconstructed over 4 climatic cycles from the Vostok ice core and over 8 climate cycles from the Epica ice core. Finally, he authored more than 100 publications, and among them more than 20 in Nature and Science. So Jean-Marc really liked to be in the field, and he contributed to many expeditions. And I guess the most important for him was the Vostok station in Antarctica. So he went 3 times, he stayed 3 times in Vostok in 92, 95, and 2001. But he was also involved in all kinds of expedition and drilling. Here you have a picture from a drilling in Col du Dôme. So you probably know Col du Dôme is just below the summit of Mont Blanc in France. He went also to Summit in Greenland. He went to Low Dome in Antarctica with the Australian. And besides this work on the field, he spent hours in the lab, and he measured, I don't know how many, but probably thousands of samples. So Jean-Marc also developed a research on snow and fern densification and on gas diffusion in the fern. And finally, he his research as the interface between snow physics and paleoclimatic became really key for a good interpretation of the record from ice core, and especially for the interpretation of gas record in ice core. So Jean-Marc had for sure a strong rigor on science, and his thinking was often critical. And I remember I had a hard time sometime during my PhD. But at the end, working with him for sure helped me to progress in my research. Jean-Marc was really passionate, I think, by his science, and it was great to work with him because you could really feel this passion, actually. And I have a great memory of that. So friendship maybe is something I have to mention here, because friendship was for sure really important for him in life. Many people at LDG would recognize him for his humanism, and many people have great memory of great souvenir with him. So over the last 3 years, Jean-Marc fought against cancer. But until the end, he kept this interest in science, he kept his optimism, and he kept his sense of humor. And today we miss, and for sure we'll miss more and more Jean-Marc. We'll miss him as a scientist, we'll miss him as a colleague, as a friend, and I hope that this furor that I had today here will also help you to keep memory of him as a great scientist, but also as a great man. Thank you for your attention.
Thank you, Xavier. I think it's a shame that we lose a brilliant scientist at the peak of his career. But, well, I'll just interject a semi-personal note. I'm older than most of you, and I've reached the point where I see people that I've known for a long time disappear. The lesson is, don't procrastinate too much, okay? Write that paper, finish that analysis. You may not get around to it. Take that trip. Okay. We are here to learn more about paleoclimatology, paleoceanography, and it's significant that we have remembered Barnola because some of his major contributions had to do with the impacts of glacial interglacial cycles. And the Emiliani lecture is an appropriate place to talk about those things. Prior to the contributions of Cesare Emiliani, there were 3 glacial interglacial cycles, the Wisconsin, the Illinoisan, and the Nebraskan, because the record of these things was on continents, and glaciers have a nasty habit of erasing their records, right? He discovered through piston core work that there were 5 interglacial glacial cycles, and of course now we know there are many more. But the procedures that he devised are the things that let us do that. He was formally trained as a 4AM micropaleontologist at the University of Bologna, which remains a bastion of micropaleontology work. And then in the 50s, we're going to be competing with this session next door all the time, so adjust to it. And they'll compete with us too, okay? In the 50s, he came to the States and worked in Harold Urey's lab for a number of years and learned isotope geochemistry. And this is a picture of him in Urey's lab. And you'll notice the isotope mass spectrometer behind him. It took up half the room. And you notice in front of him, analyzing the output from that. He did it with a pencil and a ruler. In those days, if a person could do 5 or 10 analyses a day, he was doing magnificently well. And so, of course, this constrained the output, but nonetheless, the output was novel. In the late 50s, he was lured by F. Walton Smith to go down to the University of Miami, where he spent the rest of his career and made most of his contributions that are important to us. He was, in a sense, a Renaissance man. He did many things, spoke many languages. We are interested principally in his scientific contributions and the recognition of multiple ice ages through the application of isotope geochemistry is probably the most significant one that continues to impact all of us today. Much refined, but the principles go back to him. He was also a very strong and eloquent proponent for deep drilling, scientific drilling in the oceans. He recognized the limitations of piston cores, which at those days were only 5 or 6 meters. Piston cores, of course, have advanced much, but the drilling has been magnificent, and that is what we learned so much about ocean history from. You may not know that he encouraged calendar reform, and if you Google the Holocene calendar, you will learn about it. But I will briefly tell you that he recognized that there's a little BCE and CE problem, and that is that when we go from that transition from before current era to current era, there is a 0 year. That makes no sense in a geological context, of course. So he proposed the Holocene calendar, which started, the Holocene during his era, it started 10,000 years ago. So the beginning of the Holocene was year 1, and so this year is 10,009, okay? So that's, of course, been redated now that the Holocene starts a bit earlier. He can truly be considered the father of, or the founder of paleoceanography for all of these reasons. And ocean sciences and paleoceanography, paleoclimatology have celebrated his contributions through this series of Emiliani lectures at this meeting that started in 1999 with Nick Shackleton's presentation. And you can see there's a list that will, after today, be 11 people long of eminent paleoceanographers making contributions to continuation of his work. Our speaker this year, starting the second decade of these lectures, is Delia Oppo, who is a senior scientist at Woods Hole Oceanographic Institute. Delia has been very interested in the oceanography of the last 125,000 years. She's made a lot of contributions, particularly on the eastern boundary current sides of oceans. And today she's going to tell us about the connection between the Indo-Pacific warm pool and well, I'll let her tell you what she's going to tell us about. Okay, Delia, come on up and regale us for the next hour or so. Welcome.
Well, thank you very much. Good morning. Can you hear me?
You're going to have to be close to it.
Can you hear me better now? Okay. Well, it's a tremendous privilege to give this year's lecture in honor of Cesare Emiliani, one of the founders of paleoceanography. Over the course of the next hour, I'm going to share with you insights that my colleagues and I have gleaned, by studying sediments in Indonesia and from modeling studies and putting our results in the broader context of published work. Much of the focus of my discussion will be on the Indonesian Throughflow, the connection between the Pacific and the Indian Ocean through a network of complex passages in the, between Indonesian land masses. Now, I forgot to ask, so this is just a click? Yep. Before I begin, however, I'd like to acknowledge my collaborators with whom I've exchanged samples, data, and had numerous discussions that help shape the ideas that I'm going to present today. I'd also like to acknowledge help in the laboratory from a number of people, and also Indonesian agencies and everyone who sailed on the Barunajaya 8 to the Indonesian region. The lion's share of this work was funded by the National Science Foundation, with a contribution as well from WHOI's Ocean and Climate Change Institute. The work that I'll present today builds on published work on the sea surface temperature and hydrological history of the last several millennia. However, today I'm going to present unpublished work which focuses on the last deglaciation and on Holocene orbital trends. Of Chisota's many contributions, there are two that I'd like to highlight because they're particularly relevant to the work that I'll be presenting today. In the first of these two studies, he used oxygen isotopes of different species of foraminifera to infer that they calcified their shells at different depths in the water column. In the second of these two studies, he used the oxygen isotopes of foraminifera to infer long-term ocean temperature trends. We'll build on these studies, except we're using magnesium-calcium of foraminifera to infer sea surface temperature and thermocline temperature and thermocline structure. Like Cesare Emiliani, I'll be plotting time on the x-axis going from left to right, so that the most recent sediment is going to be on your right. So I'll begin the presentation by discussing some modern observations of the Indonesian throughflow and proxies that we use for reconstructing the Indonesian throughflow. Then I will describe the deglacial response of the Indonesian throughflow to sea level rise. In particular, the opening of a gateway allowed fresh water from the South China Sea to enter the study area, and will evaluate the response of the oceanography of the area to the input of that fresh water. And we will see that there were dramatic changes in the oceanography of the area to that freshening of the region. And armed with this evidence that our proxies can record changes, dramatic changes in the Indonesian throughflow if they occurred, we then proceed to evaluate the response of the Indonesian throughflow to orbitally forced trends in tropical hydrology. Surprisingly, we find very little evidence for large changes in the Indonesian throughflow region in response to these hydrological trends. And that may indicate that our proxies are limited and unable to record subtle changes that did occur, or it may indicate that that the response of climate to insolation trends resulted in competing effects that dampened the response of the Indonesian throughflow to these Holocene trends. We were especially surprised to find no change in the Indonesian throughflow in response to postulated changes in ENSO, and so during the last part of my presentation, I will present modeling evidence that allows a different interpretation of those data that have been used to infer Holocene changes in ENSO variability. So this map shows the important elements of the Indonesian throughflow. About 80% of the 10 to 15 spherodrops of water that flow from the Pacific to the Indonesian Ocean through the Indonesian throughflow flows through the Makassar Strait, the area shown by the blue rectangle. These waters derive from the North Pacific, and they occupy the surface through upper thermocline area of depths of the Indonesian throughflow. In red denotes the flow of South Pacific water into the Indonesian throughflow, and water from the South Pacific occupies the lowest part of the thermocline and intermediate water. The green arrows denote the seasonal currents from the Java Sea, and during the boreal winter monsoon, these are fresh waters that flow into our study area. About 20% of the Indonesian throughflow flows directly from the Makassar Strait into the Indian Ocean through the Lombok Strait, denoted by the green circle. The other 80% of the flow turns eastward and then enters the Indian Ocean through the Umbai Strait, shown in red, and the yellow and the Timor Passage shown by a yellow dot. The Indonesian throughflow transfers about half a petawatt of heat annually, although that number is very poorly constrained, from the Pacific to the Indian Ocean. This heat is transferred in the upper part of the flow, and so changes in the Indonesian throughflow can impact the sea surface temperature distribution and therefore the atmospheric circulation and the hydrologic cycle. The Indonesian throughflow is very sensitive to changes in the monsoons and to interannual variability. These two panels show the temperature on the upper panel and the salinity of the 25.5 sigma theta density surface, which in the vicinity of the Indonesian throughflow is at approximately 200 meters water depth. And these figures clearly show that the thermocline of the Indonesian throughflow derives from the cool, fresh North Pacific. We can see the Indonesian throughflow as a cool, fresh tongue flowing across the Indian Ocean, and the Indonesian throughflow has been observed in agulous eddies in the Atlantic Ocean, indicating that it's part of the return flow and an important component of the Atlantic overturning circulation. There's significant water mass modification that occurs along the flow path from the Makassar Strait to the eastern exit regions. In the upper right graph are thermocline temperature profiles, and I draw your attention to the Banda C profile in green and the Makassar Strait profile in red, and the location of those temperature profiles is shown on the map below. And we see that at every depth in the thermocline, the Banda C is cooler than the Makassar Strait. And part of the reason for this is that the Indonesian throughflow shoals a bit in transit to the Banda C, but it's also related to vigorous vertical mixing, tidal mixing in the Banda C. And this vigorous mixing brings colder water from below into the thermocline. The Indonesian throughflow varies seasonally, as is shown in these mooring results from the Makassar Strait. In gray are results for the boreal summer monsoon, and in black are results for the boreal winter monsoon. Depth is on the y-axis, and the axis for velocity is the lower axis, and the axis for transport is the upper x-axis. And we're going to focus first on the velocity profiles, which are the curves. And we see that during the boreal summer monsoon, there's southward flow at every depth in the water column, whereas during the boreal winter monsoon, there's a reversal of the flow at the surface and near the surface. There are also differences in transport, shown by the horizontal bars. In gray again are the results for the boreal summer monsoon, showing that there is southward flow, that there is considerable transport near the surface, and above 200 meters or so, and then declining southward transport. And the black horizontal bars for the boreal winter monsoon show that there's much less transport near the surface in boreal winter and greater transport in the thermocline. And so on a mean annual basis, the transport of the Indonesian throughflow is thermocline intensified. The reason for this relates to the seasonal variability associated with the monsoons. So during the boreal winter monsoon, on the left are these are salinity profiles. There's heavy rainfall and runoff in association with the boreal winter monsoon, and the prevailing winds are from the northwest, advecting this fresh water to the southern Makassar Strait. This creates a northward pressure gradient that inhibits the southward flow of surface and near-surface waters. During the boreal summer monsoon, the rain has shifted northward over mainland Asia, And so there's reduced precipitation and reduced runoff in the study area, and the prevailing winds have switched directions, and they advect the saltier waters from the Banda Sea and the Flores Sea to the Makassar Strait, removing this northward pressure gradient and enabling the southward flow of surface waters near the surface. The Indonesian throughflow also varies considerably on interannual timescales, and relevant to today's talk are the variations that occur in association with El Nino. So during normal conditions, or ENSO-neutral conditions, there are strong easterly winds at the surface and of the Pacific and a strong tilt in the thermocline. There's the upwelling of cool waters in the eastern Pacific and a deep thermocline and warm waters in the western Pacific. Strong convection and heavy rainfall occurs over the warm waters of the western Pacific, and there is subsidence and dry conditions over much of the eastern Pacific and coastal South America. During El Nino conditions, the surface easterlies relax, the tilt of the thermocline lessens, it's deeper in the eastern Pacific, which warms, as does the central Pacific. And the convection shifts eastward over the anomalously warm waters of the central and eastern Pacific. And as a result, Indonesia and other parts of the western Pacific experience drought, and there are heavy rainfalls over the eastern Pacific and over coastal South America. These mooring results from the Makassar Strait demonstrate that there are significant changes in the Indonesian throughflow in association with ENSO. These mooring results go from the beginning of 1997 to the middle of 1998, and in black, solid black line, is the Southern Oscillation Index, indicating, showing that the strong El Nino event at the end of 1997. Associated with the El Nino, in the thick gray line, we see a dramatic cooling of the thermocline of the Makassar Strait between 150 and 400 decibars. Also shown in the dashed line is the volume transport in the thermocline, and there was a dramatic reduction in the transport in association with this El Nino. And in fact, one of the main reasons we went to the Indonesian region was to evaluate the response of the thermocline to postulated changes in El Nino during the Holocene. In order to reconstruct temperature and the delta-18 of seawater, we measure magnesium, calcium, and delta-18 in planktonic foraminifera. Magnesium, calcium is a function of temperature, and the delta-18 of the shell is a function of both temperature and the delta-18 of seawater. And the delta-18 of seawater is a complex but integrative indicator of the hydrologic cycle. Generally speaking, more positive values indicate drier and fresher, drier and saltier conditions, and more negative values indicate wetter and fresher conditions. There have been many studies that document an exponential relationship between temperature and magnesium calcium of planktonic foraminifera, and we will be using the calibration that was developed and shown on your left by Anand et al. They used foraminifera collected in sediment trap. They measured the magnesium calcium of many different species of planktic foraminifera, and we'll be using the single relationship that best describes all the species that they measured. And we applied this equation developed in the Atlantic Ocean to our sediment from the Indo-Pacific region. We measured magnesium calcium in two species of foraminifera, G. ruber, the photograph shown in the green frame, and P. obliqulaculata, shown in the blue frame. And we measured the magnesium calcium in surface sediments from three regions, shown by the green rectangles. And the graph shows temperature on the y-axis going from 10 to 35 degrees, and the longitude of the surface sediments on the y-axis. The Area 1 and 2 are shown on the larger graph, and Area 3, the Makassar Strait region, is shown on the small graph to the left. And the curves shown on that graph are the temperature of different depths in the water column. In green symbols are our sea surface temperature estimates for G. Ruber, and those data fall close to the mean annual sea surface temperature as derived from satellite data, confirming previous studies that in most areas, G. Ruber lives near the surface and throughout the year. The blue symbols show our results for P. obliquulaculata, and those data all fall near the 90-meter temperature. So these data suggest that we can use the magnesium-based temperature estimates of these two foraminifera to monitor changes in the sea surface temperature and in the thermocline at about 100 meters water depth. And first we look at the effect of sea level rise on the Indonesian throughflow. So during the last glacial maximum, the Sunda Shelf was exposed, so all that area shown in the lightest blue color and in yellow was above sea level, and there was no connection between the South China Sea and the Indonesian throughflow region. These two maps are reconstructions of sea level at about 10.2 thousand years ago on your left and about 9,500 years ago on your right. And they show the widening of the gateway between the South China Sea and the Indonesian throughflow area region, widening, and I've highlighted that region with the red rectangles. So the South China Sea connection was established sometime between 9,500 and 10,000 years ago, when sea level was about 30 meters lower than today. And it's been hypothesized that the opening of this gateway allowed fresh water, which drains into the South China Sea, to enter the southern Makassar Strait, and the initiation of this fresh water from the South China Sea caused the thermocline intensification that characterizes the Indonesian throughflow today. So to test this hypothesis, we first need to evaluate whether or not the salinity distribution of the region changed in response to the opening of this gateway. To do this, we compiled new and published data from 3 regions: the South China Sea, shown in blue, the Indonesian throughflow area, shown in green, and the Western Pacific Warm Pool area, shown in red. And remember that my time is going from left to right here, so, and the timing of the Sunda Shelf flooding is shown by the black rectangle. Before the Sunda Shelf flooding, the South China Sea had lower delta O18 of seawater values than the other 2 areas, indicating that it was indeed fresher because of the many rivers that drained into it. The Indonesian throughflow area was a little bit fresher than the Western Pacific Warm Pool because it also received heavy rainfall, and there are also areas that drain directly into the area. At about the time of the Sunda Shelf flooding, though, we see a divergence between the delta O18 of seawater in the Indonesian throughflow area and in the Western Pacific Warm Pool, confirming that the opening of this gateway freshened the Indonesian throughflow area. The South China Sea remained fresher, or considerably fresher, than the Indonesian throughflow until approximately 8,500 years ago, suggesting that the gateway was fully opened at about this time. So now we have strong evidence that the opening of this gateway did indeed freshen the southern Makassar Strait area. And so in the next few figures, we're going to evaluate how that changed the oceanography of the Indonesian throughflow area. So the first thing we looked at was temperature and thermocline reconstructions in a core from the Makassar Strait. The location of the core is denoted by the blue star in the map. And we do see a slight increase in the temperature gradient between the surface and the thermocline associated with this at about the time of the Sunda Shelf flooding, but we can't really demonstrate that, that these are not just the continuation of trends that began before the opening. So we take the conservative approach for now and conclude that there are no abrupt changes in the thermocline structure of the Makassar Strait associated with this opening. And this contrasts with data from the Timor Sea, the core location shown in blue. Published data from this core suggests that before the Sunda Shelf flooding, there was about a 6-degree temperature gradient between the surface and the thermocline, and after the flooding, this gradient increased to about 8 degrees C. And this core is located near the thermocline depths. Are near a gradient between the warmer, saltier Indian Ocean water and the fresher, colder water of the Indonesian Throughflow. And so these authors suggested that with the thermocline intensification of the Indonesian Throughflow that occurred as in response to the flooding of the Sunda Shelf, the Indonesian Throughflow displaced some of the warm Indian Ocean thermocline water. Now, we generated data from a second core near a different exit passage. The data shown in green, as is the core location. These data are this core site is downstream from the Indonesian Throughflow that enters from the Umbai Strait. And these data also show a sharp cooling in association with the flooding of the Sunda Shelf. And perhaps the more another way to look at these data is to compare them to the thermocline temperature of the Makassar Strait. And it becomes clear that prior to the Sunda Shelf flooding, there was a smaller gradient between the Makassar Strait and the Savu Basin than there is today, actually. And so that the modern gradient between the Makassar Strait and the exit passages was established once the once the Sunda Shelf was flooded. And to evaluate the factors that may have contributed to the enhanced downstream cooling, I refer back to the mooring results from the Makassar Strait. So prior to the flooding, there would have, once the flooding occurred, there would have been reduced transport of warm waters above 150 meters. So if we look at the winter profiles for analogy, and there would have been greater transport of cool waters below 200 meters. So these factors alone would have indicated that there would have been cooler waters mixing in the Banda Sea. However, the fresh water in the southern part of the Makassar Strait may have also influenced the residence time and therefore the time available for mixing and water mass modification in the Banda Sea. So prior to the flooding, there would have been rapid flow of warm surface and upper thermocline water through the Banda Sea to the exit passages, and there would have been little time for water mass modification and cooling. After the flooding, the residence time of surface and upper thermocline water in the Banda Sea might have increased because there was not this rapid flushing of the water out of the Banda Sea. By the water flowing from the Makassar Strait. And so there would have been more time for vertical mixing in the Banda Sea and cooling. So now, armed with this evidence that that our proxies can record large changes in the Indonesian throughflow if they occurred, we proceed to evaluate the response of the Indonesian throughflow to orbitally forced changes in the hydrologic cycle. In the upper panel are curves of incoming solar radiation for boreal summer and boreal winter, and in the lower panel for what am I saying? So in the upper panels for 30 degrees north, boreal summer and boreal winter, and the lower panel shows the summer and winter incoming solar radiation for 30 degrees south. And what we see is a decrease in the seasonal cycle of incoming solar radiation since the early Holocene in northern latitudes, and an increase in the seasonality since the early Holocene in southern latitudes. And these changes affected the monsoons and have been postulated to affect Pacific mean state and ENSO. This graph on your left shows important proxies for hydrologic change in the area. These these curves are arranged from north to south, and the location of the individual records is shown by color-coded stars on the modern January precipitation map. Wet is up on all these curves, and dry is down. And the upper three curves are speleothem delta-18 records. The green curve is a record of titanium calcium, an indicator for runoff, and that core comes from the south of Java. So if we focus on the peak rainfall in each region, we see an orbitally forced trend that goes from forward in time from north to south. Now, the lower curve is the delta-18 of seawater from our best record from the southern Makassar Strait, and we wouldn't expect the delta-18 of seawater from the Makassar Strait to look like any single precipitation record, because it's not only affected by local precipitation, but it's also affected by the advection of currents from many directions. However, if we look closely at the records, we'll see that it does contain features of the two southern Indonesia records, so that would be Flores in orange and South Java in green. So from about 10 to 7,000 years ago, there's a decreasing trend in the delta-18 of seawater, so a freshening. And this is related to both the Sunda Shelf flooding and the increase in precipitation that is seen over Flores. There are increasing delta-18 of seawater values, or increasing salinity, from about 6 to 3,000 years ago, associated with that relatively dry interval over Flores. After about 3,000 years ago, there's a freshening trend associated with this westward shift or westward expansion of precipitation that's recorded in the South Java core. So in the next figure, in this figure, we wanted to evaluate whether these changes in delta-18 in salinity in the southern Makassar Strait influenced the temperature gradients in the Makassar Strait, in the Indonesian Throughflow area. And we focus on the late Holocene freshening trend because it's the most pronounced trend since the flooding of the Sunda Shelf. And we see that there's no obvious correlation to downstream temperature trends based on the modern seasonality and the evidence we have from the Sunda Shelf flooding. We would have expected an increase in the temperature gradient if the freshening was increasing the residence time of waters in the Banda Sea and therefore enhancing vertical mixing. So So there are a few possibilities. One is that there are limitations of our proxy, and that there were, in fact, changes in the Indonesian throughflow that were too subtle to record by our approach. And the alternative is that there were competing effects, other climate changes that occurred that dampened the response of the Indonesian throughflow to freshening in the southern part of the Makassar Strait. We also want to evaluate changes in the Indonesia area in response to postulated changes in ENSO. And so I'm going to review some of the more compelling evidence for changes in ENSO variability during the Holocene. This is a picture from a study of a marine sediment core from the eastern Pacific, and I show its location on the El Nino sea surface temperature anomaly map for December 1982. And you can see that this region experiences dramatic warming during El Nino events, and it also experiences cooling during La Nina events. In this study, Tom Kutavas and his colleagues generated oxygen isotope data on many individual foraminifera from 2 time slices. They used 2 samples from the mid-Holocene and 2 samples from the late Holocene to evaluate the change in variability. And if you saw Tom's talk earlier this week, you'll know that he has filled this out and confirmed these results beautifully. And the data show an increased variability in the late Holocene relative to the mid-Holocene, and this has been inferred to be the result of both an increase in seasonality and an increase in interannual variability during the late Holocene relative to the mid-Holocene. On these graphs, I show data from 2 lake cores. This is an old version. I don't know how I did this. Both these cores come from the eastern tropical Pacific, and their location is shown on the precipitation anomaly map for El Niños, and both these areas experienced a dramatic increase in rainfall in association with El Niño events. And in these lakes, there's a sedimentological response to intense rainfall events. And in gray are the data from a lake in the Galapagos, and El Niños are recorded by increased percentage of sand. And in red are data from a high-altitude Ecuadorian lake, and during El Niño events there are inorganic clastic layers, and both these records show that there was dampened variability during the mid-Holocene relative to the late Holocene, and these two have been inferred to indicate an increased frequency of El Niño events during the late Holocene relative to the mid-Holocene. There are also data that suggest a change in the temperature gradient between the eastern and the western Pacific. The core locations are again shown by red and blue stars on the 1982 El Niño sea surface temperature anomaly map. In red are data from the western Pacific, and in blue are data from the eastern Pacific. And you'll note that I've plotted each record on its own axis for clarity. And there was a 7-degree temperature difference in the mid-Holocene, and this temperature gradient decreased to about 5 degrees at about 3,000 years ago. And these data have been suggested to indicate that the Pacific was more La Nina-like during the mid-Holocene and more El Nino-like during the late Holocene. And so now we'll evaluate whether these postulated changes in ENSO or mean state had any influence in, or had any clear signature in the Indonesia area. So again, I'm showing the anomaly map, the precipitation anomaly map, and we see that Indonesia is in an area that experiences drought during El Niños, and we've already noted that there was a freshening in the late Holocene at this time when there may have been increase in the frequency of El Niño events. So this is opposite of what we'd expect, and it may indicate that on this time scale, the effect of the monsoons is more important than El Niños in affecting the hydrology of the area. We also looked at the temperature gradient between the surface and thermocline of the Makassar Strait. You'll recall from the mooring results that the thermocline of the Makassar Strait cools dramatically during El Niño events. And yet we see no change in the temperature gradient between or no dramatic change in the temperature gradient between the mid-Holocene and the late Holocene. It's approximately 6 degrees Celsius throughout our study interval. And so these data suggest that either there are limitations of our proxies that we can't record the subtle changes that did occur. However, they also lead us to the last part of my presentation, and that is to evaluate alternative explanations for the data from the Eastern Pacific that suggest enhanced variability, enhanced interannual variability during the late Holocene. So to do this, we look at results model simulations using the GFDL Ocean Atmosphere Coupled GCM, the latest version CM 2.1. And for details on the models and model biases, you can look at these two papers published in 2006. We're going to look at two simulations, the mid-Holocene simulation and the pre-industrial simulation. And the only difference between these two simulations is the insulation forcing. In the graph, we show the spectra of the Niño 3.4 sea surface temperatures. In black is the pre-industrial, in red is the mid-Holocene run, and we see two important features. We see a dampening of the seasonal sea surface temperature cycle in the Niño 3.4 region, and this is a feature of all published 6K simulations. In red, we see enhanced amplitude of interannual variability during this mid-Holocene compared to the pre-industrial. Now, this is not a feature of all published simulations. Most publications report a dampening of El Niño variability in the mid-Holocene. However, I refer you to this graph from the IPCC report, which shows the results of global warming simulations. On the x-axis, we see that most of these model simulations suggest that the future sea surface temperature pattern of the Pacific will be more El Niño-like, but there's absolutely no consensus on the y-axis as to whether the future Pacific will have more interannual variability or less interannual variability. So this leads us to conclude that we can't yet, from modeling studies, infer whether or not there was an enhanced or reduced interannual variability during the mid-Holocene. But this modeling simulation gives us the opportunity to explore whether we can explain the published data from the Eastern Pacific as only a result a response to the dampened seasonal cycle, since in this model there's actually an enhanced El Niño during the mid-Holocene. So in this figure, we look at the amplitude of the seasonal sea surface temperature cycle throughout the tropics, and we see that for all latitudes south of about 5 degrees north in the Pacific, there is a reduction in the amplitude of the seasonal cycle, and for all latitudes north of 5 degrees north, there was an increase in the amplitude of the seasonal sea surface temperature cycle, and this is what we would expect from precessional forcing. In the lower left panel is the seasonal sea surface temperature cycle for the area between 5 degrees north and 5 degrees south at the equator. And in blue, in the right panel is the mid-Holocene sea surface temperature anomaly, the seasonal cycle of those anomalies. If we focus on the right portion of both those two lower graphs, we see that there's a cooling, shown in blue, of the warm season, and there's a warming, shown in red, of the cool season. And this is why there's a reduction in the amplitude, confirming the reduction in the amplitude of the seasonal cycle. If we look at, so now we're going to focus on the proxy data. So the rainy season in this area is the warm season, DJF, and actually into March. And on the upper panel, we have the sea surface temperature anomalies for DJF, showing a dramatic cooling of the warm season in the cold tongue. Actually, it's in the entire Niño 3 region. And in the lower panel are precipitation anomalies, and as a result of this cooling, there's a reduction in rainfall during the rainy season. Now, to compare more directly to the sediment core data, we want to look at events. So to do this, we specify precipitation thresholds ranging from 2 to 14 millimeters per day. And we look at 100 years of simulation in each the pre-industrial run and the 6K run, and we compare the number of months where there are precipitation events that exceed that threshold in both the pre-industrial run and in the 6K run. Oh, how do I go back? So if we focus, for example, on the 4 millimeters per year, and we look at the Galapagos, we see that there are 40 months that precipitation threshold is exceeded in the pre-industrial run, whereas there are only 15 times that threshold is exceeded in the 6K run. Yet the 6K run is the one that had more interannual variability. Similarly, if we focus on the Ecuadorian Andes site, and let's look at, say, 8 millimeters per day, we see that there are 422 times that that precipitation threshold is exceeded in the pre-industrial run, but only 230 times that precipitation threshold is exceeded in the 6K run, even though the 6K run is the one that had more interannual variability. So in this model simulation, the reduced amplitude of the seasonal cycle is more than compensating for the enhanced interannual variability. Similarly, we can look at the frequency of monthly sea surface temperature values from these same 100 years of simulations for the core location of this study of variability, sea surface temperature variability. So this is near the Galapagos. And on the upper panel are the frequency of sea surface temperature values for the pre-industrial run, and on the lower panel are the frequency of sea surface temperature values for the mid-Holocene run. And we see that in the mid-Holocene run, the data are clustered more towards the center of the distribution, whereas there are more data towards the tail of the distribution, or there's a broader range of variability in the pre-industrial run. So these data are also saying that are suggesting that in this simulation, the reduced amplitude of the seasonal cycle is more than compensating for the stronger interannual variability. And these results look very similar to results from a model simulation in which there actually was reduced amplitude of interannual variability in the mid-Holocene. And so these results are suggesting that variability in the eastern equatorial Pacific is not diagnostic for changes in ENSO during the Holocene, that we can explain the data just as a reduction, just in response to orbitally forced changes in the amplitude of the seasonal cycle. So to summarize, we began the discussion by looking at the response of the Indonesian throughflow to large changes in salinity distribution in the southern Makassar Strait in response to sea level rising. We were able to show that there were dramatic changes in the Indonesian throughflow in association with this freshening. However, during the Holocene, these same proxies, we didn't see any large changes in the oceanography of the Indonesian throughflow, suggesting either that there are limitations of our proxies or that there are competing influences that conspired, so to speak, to dampen the variability in the Indonesian throughflow. We were especially surprised not to find changes in association with postulated changes in ENSO, since that was one of our main motivations for going to the Indonesian throughflow area. And so I presented model simulations that suggest alternative ways to explain the data from the Eastern Pacific, suggesting enhanced late Holocene variability as a response to insulation force changes in the amplitude of the seasonal cycle. Thank you.
Okay, we have time for some questions or comments. I'm going to let Delia decide who she'll respond to, so you can
put on my glasses. Any questions? Yes?
I have a question about comparison to search for
Yep.
So I wonder if because forums are animals, they want to live where it's travel. Do you think it's possible that some of the results slightly affected by the vertical migration and maybe that's
Yeah. I'll repeat the question. So the question is whether or not, since forams migrate, since they're animals and they migrate throughout the water column, is it possible that that there are changes in the depth habitat of the P. obliculata in particular that are obscuring changes that did occur? And the answer is yes, that's possible. One of the reasons we did this core top calibration across different areas, different oceanographic regions, was to see how robust its depth habitat was to different changes, to different oceanographic conditions. So it lived, that foraminifer in today's sediment occupy the approximately 100-meter depth level in both strong upwelling areas, strongly stratified areas, and intermediate areas. That's not to say it didn't happen, and so we are pursuing other proxies for looking at thermocline structure. Any other questions? Well, thank you.
Okay, well, we have a small souvenir for Delia that she can help you remember this morning. And thank you everyone for coming. We have posters.